I'm glad to be back in person meetings. And I'm very glad to see a lot of faces I haven't seen in a while. You know, a year and a half, 2 years ago, when this COVID-19 hit, you know, we didn't know what was gonna be on the other side, so I'm really glad to see some faces here. Folks that I haven't seen in a while. So I'm really, glad to just see them. For those of you who don't know me, I'm James Link, president of a local, Nashville chapter of the National Society of Automation. And, I'm president, and Penny, there's, vice president. Our treasurer, Mark Goldstein, he's on the line tonight, he's remote. So, daughter's getting married this week, so we gave him a break, not to be here. Our secretary, Bob Lindeman, sent me an email yesterday, he wasn't feeling well. So, he's not here with us tonight, and our program chair, Stan Spence, is traveling. But, I'd like to take the opportunity to thank Mr. Larry Gray here for setting all this up, making arrangements for us to have this room tonight. And this presentation, so I want to recognize Larry for doing that for us.
Welcome. Anytime.
Tonight we have a presentation on vision systems applications. Our speaker is Mr. Alex Bird. Alex has been selling, and he works as a product sales engineer for Cognex Corporation. Alex has been selling and supporting 2D and 3D vision systems in the Southeast for over 10 years. He's visited over 700 manufacturing facilities and has extensive knowledge in incorporating machine vision to the factory floor. Currently resides in Franklin, Tennessee, and covers the geographic area of 6 states from Kentucky to the Gulf Coast. So, Alex, just Jim Link. I've already introduced you, so if you want to take it from here, you can go right ahead.
Okay, great. Once again, how is my audio coming through?
We can hear you fine.
Good. Okay. Thank you very much for the introduction. And as I think I overheard earlier, I was hoping to be there in person. However, today I wasn't feeling too well, so wanted to do the prudent thing and broadcast remotely as to not share my unfortunate feelings with everybody else. So, yes, I am the sales specialist for our deep learning as well as 3D. But today, based on what is the hottest and the most promoted technology within Cognex at the moment, we're going to focus just on the deep learning D900 side of our product portfolio. Do you all have a visual of the screen?
Yep.
Yes.
Okay. Excellent. Just quick note, I'm going to be recording the call. Go ahead and do that now. Okay, so just a little background initially on Cognex for those of y'all who aren't familiar with us. We're trusted by over 25,000 customers globally. We just celebrated our 40th year in business. Over $811 million in revenue in 2020, with a near-term goal of reaching $1 billion in revenue. And we have global offices in over 20 countries. We have a tech center here in Franklin that hosts some of our application engineers. It's also got a wealth of Cognex products, and we can do a lot of research and product testing and those types of things at that facility. We also have 500 plus channel partners and are over 3 million systems shipped. Just a little visual of some of our products that we offer, whether it's mobile computer solutions, whether it's handheld barcode products, miniature vision systems, 3D vision systems, as well as our standard 2D fixed mount barcode readers, our mini vision sensor product line, and then our PC vision line, which is more or less where we're talking about the VIDI and our artificial intelligence. So, and I can't see the room there, but overall, is there any general familiarity with machine vision, or are there any people in the audience who are not familiar with vision?
You got a lot of nodding heads.
Okay, so mostly familiar, but just to kind of, a recap, if you will. So traditionally, and before vision was in practice, we would have operators using their eyes and their brain to look at a product and say, this is conforming or non-conforming. And as vision has matured, we have developed algorithms and filters to use in a CMOS or CCD camera to capture that and process what a human would in software. So now we want to differentiate traditional machine vision, which we've had that technology for the last 40 years, with artificial intelligence, which is kind of the new buzzword in all the industries. But the way that we use it is for, strictly for the factory floor. And it departs from our previous kind of understanding and methodologies for vision. So traditional vision, you've got a rigid set of rules, whether you're putting down a blob tool or an area tool or a pattern tool, you're placing a part, observing that part, and you're finding like a minimum and maximum binary value or a minimum pixel count or something where there's a hard value that you code into the system. So, and I'll reference this a little bit later in the demonstration, but when the real world variables start to change slightly, those hard-coded rules can diminish and you have to go back and make adjustments to those rules. Whereas with artificial intelligence, we're kind of departing from the rule-based hard coding vision to let's just show it good images, bad images, label those images, and have the software learn for itself. So we're going to unpack that a little bit more in the slides in the demonstration, but just trying to set the stage. Some of y'all who nodded when going through this, you might just temporarily want to forget what you've learned previous about conventional vision, because this is going kind of to a new land. So here's three spheres that kind of show the subsets of machine learning or intelligence. So we've got first the broadest, where a lot of different components fall into, is which is just AI, which is a program that can sense, reason, act, and adapt. Then a subset of that is machine learning, algorithms whose performance improve as they're exposed to more data over time. And then where our products are positioned would be in the deep learning sphere, which is a subset of machine learning in which multi-layered neural networks learn from vast amounts of data. So this is going to most closely mimic the capabilities of the human mind. So then this is kind of visualizing what I mentioned or started to mention earlier. So traditionally we've used humans because when they're not with a cold like I am and they're sharp, they can perform well. They've got flexibility. They can learn new things, but they also can make mistakes. And on the opposite side of the coin, you've got the reliability and consistency of computers, but they only are as good as what you tell them, and they can't reason, they can't look at things from multiple perspectives. It's just, it's binary. So the positioning of this product and this technology is somewhere in the middle, which gives you human-like performance, but also the consistency. Once it's trained, it's going to repeat the same time over and over like a computer. So the easiest way that I can explain this is the example of teaching a toddler what a house is. So I've got a 15-month-old daughter. She's probably running around downstairs right now. And if I were to teach her what a home is, conventional style would be to say a home equals a front door, a two-car garage, a driveway, a 4 windows and a lawn. But that's not the way you would teach a child. You would just drive them down the road and say, this is a house and this is a house. This is an example of another house. They all look different. That's a Chuck E. Cheese, and we can't stop there today, honey. I'm sorry, but that's a house. And then when they see enough of those different homes, they can understand what a house is, and they can also predict and draw you a house. So another way of looking at this would be how you would train a computer, a conventional computer, what a cat is. So we input the image of a cat here, and the computer says, okay, it's got 2 pointy ears, two eyes, a nose, a wide body, and a bushy tail, right? So that equals a cat. So that's great. We can draw the edge vectors of this cat with a pattern search, PatMax Redline, whatever it is, and we can compute that this is a cat every time pretty well. But what happens when the next cat looks like this? It's still a cat, but the computer is going to have no way of determining that that's a cat because it's a different color than what we've trained, it's a different shape, and there's no contrast because this cat is sitting on this white leather couch. So what the computer ends up seeing is this kind of, highly convoluted 2 patterns, and it's not going to be able to pass this. So then you have the cats that come in looking like this, all these different cats. So you get the point. Cats can look many different ways, but how could we train a computer, to see a cat in all these different variations? And the answer is we do that by using an abundance of data, and we push that data into a highly powered PC, which then will basically send all of those data points through a neural network. And there's some advanced formulas that go into that. There's also a lot of neural network information on YouTube that it takes quite a while to get through it. So I'm not going to spend too much time on the exact math of this portion here. But there's a wealth of information out there on neural networks. And at the result, what you get is the input variable is your image. It breaks that up into little nodes, passes them through, and your output is, yes, I've identified this as a cat. So now we move into our specific tool and examples of, in the machine, the factory automation world, machine vision world, how we can aim at some of these things. So our D900 is our deep learning enabled smart camera. So it has all of the capabilities to fully use these algorithms within. We want to position this product and this technology for 3 key things within vision inspection. Those three key things are defect detection, assembly verification, and optical character recognition, or OCR in short. We also have 2 modes of this camera. We've got a 5 megapixel and a 2.3 megapixel mode. And I'll show y'all in the demonstration how this is programmed in spreadsheet. So, traditional examples of when we would look for defects would be this VIDI detect tool. Types of things that it can see are like scratches, dents, dings, improper soldering. You can see here, this is an otherwise, non-uniform background, but you can see that scratch right there. Improper, weave right here. This is just missed a stitch. So what you'll notice between all of these things is they're all visually identifiable. We as humans can easily just see them really quickly and say that's the issue. However, with all this different contrast, you've got light spots, you've got dark spots, you've got curvatures, varying textures, you've got this little clip in the middle, then you've got all these zigzag patterns. All of these things make putting conventional tools down very difficult. But one thing to note with any of our deep learning tools is the guiding principle is if you can see it, we can train the camera to see it. And it's example based. So if you have examples of good parts and defects, we can train the system to find them. So optical character recognition, or OCR, this is actually how Cognex got started in vision 40 years ago, reading characters on different like PC boards and circuit chips and those types of things. And back then it was cameras are going to these large computers, and there were so many pieces of periphery necessary. And now we're on this little embedded smart camera. But the goals haven't changed that much, where there's customers that are putting characters human readable on product, and whether it's a date code or a lot code for food, traceability, or whether it's serialization of some highly complex part, those needs still exist in the world. And a challenge has always been, well, what happens if my text doesn't have high contrast? Or what if it's on this bag and it's actually fluid as it's moving around? That's where traditional vision has failed, but our ViDi-Read artificial intelligence is much more able to read those characters. And I've got some pretty shocking examples forthcoming, some videos that I can show above and beyond this. So then the third avenue would be ViDi-Check. So this is partially something that our traditional tools can do, but they can't do nearly as quickly and efficiently. But this also is opening up for opportunities that we weren't able to do in the past. So an example of something that we've done before with conventional vision is the fuse box. We can put a PatMax tool on each of these and a color tool on each of these and establish that the correct fuse is in the correct, location. However, that usually takes nearly the entire available program of information to build out all those tools. And with the deep learning, we can simply do it in one tool, and we add what's called a layout model. So we just train that this is layout A, and we show what each of these components are and where, and the system will learn through example where those locations are, and it'll be able to tell if you've got the wrong fuse in the wrong location. So then another popular one that I've seen in a few different assembly facilities is the correct components on the door interior. So whether it's chrome versus matte pull handle, or automatic versus manual on the switching, different types of trim, different speaker grills, all those types of things we can check with this ViDi-Check tool. And then we've got a medical clamshell. This one you can see here, it's pretty low contrast. It's kind of hard to see all of these different components in here. But with ViDi-Check, we're able to go in and identify that all of those are there and correct. So this is just kind of a recap on the differences between standard vision and deep learning. And I failed to mention this at the beginning, but I'll go ahead and mention now since it's appropriate. So of course we've had conventional vision for 40 years, and now on the last couple of years this AI has come into the forefront. Our investment in this this AI style product through strategic acquisitions, as well as our own R&D spend. We typically spend about 18% of revenue on R&D. So we've invested a significant amount, probably exceeding $250 million at this point in our deep learning technology. But that doesn't mean that we're abandoning conventional vision. And this slide is good to understand if you have opportunities, where we want to guide those opportunities for which types of technology. So if you're looking at gauging, measuring, barcode reading, simple presence absence, and robotic guidance, those things are all going to stick with traditional vision. The AI is not a measurement device per se. We're not going to want to use it for robot guidance. It doesn't have the ability to read 2D barcodes, although it does read human readables. But where you do want to start looking for AI as opposed to traditional vision would be really complex cosmetic inspections. If there's like textured material and you're trying to classify it or look for defects, definitely assembly verification, any deformed features, variable feature location if it's moving around, and then challenging OCR. And then of course here you can see there's stuff in the middle. If there's black text on a white background, high contrast, it's not variable. That may be perfectly fine for a conventional OCR. Some things like counting, if there's not a lot of variation, it may not take a VIDI tool to find that. You may be able to do it with a standard pattern tool. So we certainly aren't abandoning the technology that we had. We're adding a technology that allows us to do things that prior vision had struggled with and do them better, or take things that we've traditionally punted on because we didn't have the technology and now address them with our deep learning. So quick overview of the product, and this is actually the product that I have a live demo for, but this is the D900. So again, it's both 5 and 2.3 megapixel. It's monochrome in color. This is an IP67 rated unit. It's got our ARM processors built into the unit. So this is your all-in-one camera. It can't train the neural network. That's still, you rely on a PC, a GPU-enabled PC for that, but it can deploy the network. So when you're done programming, you can disconnect from your PC and this will run standalone. Nice neat thing here, we've got a IP67 body with wraparound pass-fail light. So this can be an indicator like a stack light for the operator. It'll show you either red or green. You've got your onboard storage, power and I/O cables down here, so you can go out to your PLC. You've got an external light connector, so if you don't need the integrated light and you need a backlight or a bar light or a dome light or some other specialty lighting, we can control that off the unit as well. Okay, so ahead of the demo, I want to just show you guys the cards that I have that will give a framework of why I'm showing this and why it's important. So on this screen, you can see I've got a simulated, I've got these here. There's these simulated business cards, carbon fiber business cards. And you can see that we've got hot spots, we've got dark spots. And as I thumb through these cards, that texture is changing. And on your no goods, you've got this one little stitch that is out of place. Where is it? That one right here. So if I was trying to do this with a conventional system, I don't know how I would find those defects because they're of no greater contrast than, the rest of the feature. You can't put a pattern on them because the pattern repeats itself hundreds of times. There's really no good way. And in fact, we've tried, to do this and capture it with conventional tools, and it ends up being very difficult to do so. So these parts they do a good job showcasing two things, one of which would be your part-to-part variation in that every part is not identical to the next, and also your varied lighting where you can see, different hot spots, different dark spots on here. So with that said, the task of this demonstration is going to be to find those defects on the card without ever showing the defects to the software. So I mentioned VIDI is example based, and it's got two different ways to learn. It can learn by you showing it a wealth of good examples and it'll learn what a good part looks like and automatically find errors. Or you can train it on here's good examples, here's bad examples, and it'll go looking for those bad examples. So in this case, we're going to use the former. Now, I want to give you guys a brief overview of the software really quickly. This is Insight Vision Suite. So this is where we can do all of our programming. On the left, you've got an image. And if I put this into a continuous and turn on my demo camera, you can see that now I've got a live image. You can see I've got my card right there. Go ahead and turn that off. So that's my live image. This is my spreadsheet. I'm sure those of y'all who are nodding your heads familiar with Vision have seen spreadsheet at one juncture or another. It's the most popular method of programming vision systems in the world. And it's what all of our traditional cameras run on, as well as now our video cameras. So what I've got here is my tool palette. And one thing that I'll point out, I spent a decent amount of time explaining the differences between when you would go conventional vision and when you would go with deep learning. And one thing to note, with our deep learning Insight cameras, you do in fact get all of your traditional tools. So if you needed to do some type of cosmetic inspection with deep learning, and you also needed to get the measurement, of something, you can do that by adding your deep learning tool and your traditional tool into the same spreadsheet. So I've actually done that for this demonstration because I'm going to use just a standard pattern tool to find my Cognex logo. So as I move this around, you'll see my crosshair is going to follow. Okay, so now I'll show you guys how the deep learning works. I'm going to first pull in my video detect tool. It's going to open up my property sheet. And when I want to fixture, I'm going to double click this fixture and I'm going to point it to my pattern. So this is going to allow me to track my card as I move it around, and this video tool will follow. So now I'm going to set my region of interest where I want to look. I'm going to pull out my graphics. I'm going to click OK. So I mentioned that VIDI is example based, so we need to give it examples. I'm now going to click my record button, and I'm going to populate my database. Notice that I don't really care to get these in the same position because my pattern tool is helping compensate for that. And then also I mentioned we are not going to show it any of the defects, but while training to show everybody how the scoring and labeling works, I am going to train it on something else that is indeed bad, just not the defect that we're looking for. Next, I can go in here and I'm just going to rename these. This step is not necessary if you only have 5 images. However, in a lot of cases, I've seen projects where there's hundreds to even thousands of images being trained in the neural network. And if you have these images file named as the right, status, good or bad, it makes the next step significantly easier. So I just wanted to showcase it. So the next step is I'm going to go into my video tool. And now it's opened up my tool. I'm going to drag these images into the video tool. And as you can see, it's corrected all of those images so they now perfectly align. And if I had those hundreds or thousands of images, I could simply, sort by the file name. So now these are all good. All I need to do is label these views as good and add these views to training set. Now I'm going in and I'm going to label this view as bad, but I don't need to add it to training set because in this example, I'm only training on good images. Now I'm going to click the brain button, and what this is going to do is it's going to turn on my GPU and it's going to process all of this image data. The process timing depends on, the level of GPU that you have. Some of them can take a few seconds up to a few minutes. So we'll let this go. And while that's doing that in the meantime, I'm going to jump back and show some more practical examples that I promised. So go from current slide here. So I mentioned really difficult OCR. This is what I would refer to as a 0.0, meaning traditional vision would likely have a 0.0% read rate if we tried to make this work with these images. So what we've got here is a little can of seasoning and some Best Buy. That one says January 19th, 22. Not sure what the H is for. But you can see it's very difficult even for the human eye to see what's written there. And you've got an inkjet dot print, so the characters are not solid and continuous. You've also got varied location of that print, and then you've also got this halation in there and the changing of materials. So everything about this makes it difficult. But since VIDI is example based, all we had to do is show it examples of what those characters can look like in various areas. And it's now got the capability to read those characters, regardless of where they appear, on this little tube of seasoning. This is another good one. This is something that I've done in person to a lot of different customers. This was on our mobile trade show for a period of time. This is a K&N style air filter. And basically, we just took a good filter, set it on a turntable, spun it a few times, took images and said, all these images are good. Then we put in a filter that we've dinged up and messed up a little bit. And you can see as it's running, it's able to pick up these specific areas where it's defective. And if you zoom in, this is another one similar to the card. Like in the 7-8 years I had conventional vision before I was doing VIDI, I wouldn't really have a good way to locate these features. It'd just be very complicated to use conventional tools to do so. And if you did, they would really be fragile and prone to breaking. So extremely impressive that we can do this by just spinning a few good pieces and then putting the bad pieces in, and it automatically finds what we're looking for. Okay, I got about 2 minutes left on that one. I'll share some other examples. Let's see, this is a really neat one. So we've got a PCB. This would be another one that with conventional vision would take a lot of tools, a lot of programming, because we could do a pattern find to get the gross location of the feature. And then we could use little patterns precisely to check each component that it's present, and then an OCR tool to read the characters. However, that would take a lot of different tools and a lot of programming. Well, with deep learning, we're able to do all of this with two tools, basically one for defect and then another to read the code. So in this instance, you can see that area showed up as red. It was missing a component. We scroll over here and you can see, okay, I've got these characters, low contrast, but we can read them no problem. And then we go to another one and we see, okay, the component is present, but it's just been soldered a little bit out of skew. So if you had a pattern looking for that, it might actually pass it. You would also have had to put in some rotational tolerances as well. We'll do one more here. So this would be a VIDI check example. So spark plug, verification, basically, populating all these plugs. We want to count that we've got 16, and then we also want to determine what model we have. So there you can see now we're finding silver. We choose the silver as the one we want. Now we've got all of them. And this HMI is something that we can build custom. So all of our D900s have built-in web servers. So if these cameras are out on the line working, you can tap into the IP address of that camera and see this screen that we can custom build and have operator inputs like we've done here. Okay, great. We are done programming, and now I've got some results. So as you can see here, we found my pen as bad area, but there's also some stuff going on here, a little bit of stuff here and here. So this is why I wanted to take that extra image to show you guys how scoring works. I'm going to open up my database overview, and you're going to have a confusion matrix. What you're going to see here is a score. Now, these numbers, depending on your application, these numbers are going to change. This is your distribution of how far off a perfectly good versus a horribly bad sample are. And these numbers will vary application to application. But what you would want to focus on is, do I have gray area or separation between my good and bad? And then, how does my distribution curve look? So if I take these limits and bring them off of the edge, now when I come back here, I've eliminated the little bit of noise that you see in those examples, and it's really only found the truest bad of the bad of this. So now that I've got that set, I can come back to my spreadsheet and I can insert the data into the spreadsheet. Just take a moment. Okay, now I'm going to set this as my watch cell, which means it's going to be my pass-fail bit. And then I am going to publish this cell. And go online. Oops. Let me retag those graphics real quick. Okay. There we go. Now you'll be able to see what it sees. Okay, so that's our okay image. Another okay image. Another okay. Let's see what happens when it's upside down. Still okay. So now if I turn these over, you can see automatically without ever seeing that defect, it's locked in because it knows this is not like the pattern you trained me, or it's not like the product you trained me. It's completely different. And it'll find it upside down. If I take this and got to get it in the field of view, but I can take this and I can move it up, tilt it at an angle, you know, such that my hand can get under there, move it around. So this is the part, you know, this could never be done with a conventional vision system, especially having never seen what the defects look like. So again, you know, that example is used to show you how easy it is to program. Basically, all I did was label known good images and then supply it a defect for reference. You know, no custom scripting, anything like that. Everything was programmed in the spreadsheet. Really is intuitive and user friendly to get into a deep learning opportunity. Oops. Jump back into the slide deck here. So this is just kind of a graph that shows your development effort. So usually with conventional vision, you can get results very quickly, but those results may not hold because typically you grab your part, you set it down, you observe it. That's good. Then you grab your bad part, you put it down, you observe it, you find the differences, you code in those limits, and you're on your way. But then 2 weeks down the road, your parts look a little bit different, maybe different supplier materials, the lighting's changed, whatever it is, and you go back in and you change those values, you change those rules. And that's when your performance starts to deteriorate and you're putting more and more effort into keeping your vision system afloat. And that's why you hear the age-old adage like vision's difficult to work with. So with deep learning, we hope to get around that by front-loading our development effort. You have to get all of these images. You know, if it may be hundreds or even thousands of images, you have to find examples of what you're looking for and have parts present. But once you do that and you train everything together, you can hit your required threshold of performance and you can kind of rest easy knowing you're not going to have to go back in and mess with it ever again. So that's kind of, you know, what this curve shows is it's designed to be put the effort up front and then be hands off the vision system. So, and then I made mention to this earlier, but we train and develop the application in spreadsheet on PC. Then we deploy it to the smart camera for runtime. And then project evaluation. This is something that, you know, myself and some of my counterparts were happy to do testing. If you want to do VIDI read, VIDI check, VIDI detect, any of these types of things, we're happy to do evaluations for you. Reach out to myself or any of your Cognex personnel, and we can certainly help with that. So that's everything I was prepared for. I do have one more example. If y'all would, since we've got 15 minutes, I'm happy to share one more example. This is a slightly different tool, a slightly more entry level, but very easy to use technology. What do you guys think? You want me to go into that, or do you want to go straight into Q&A?
I think you can go into that.
You want me to show it?
Yeah.
Okay, absolutely. So I took y'all through the VIDI tools, which is, those are our true AI, like high-end tools. We've also come out with a tool that may play more into that second sphere that we talked about earlier, but we have a tool called AutoLearn. So this one is only available in a classify, but it's very elegant to use and program. And I'll show you all that here. So we have vehicle roof, and we're going to be looking for sunroof, either no sunroof, one sunroof, or two sunroof. Now, what y'all will notice on this image, terrible lighting, reflections everywhere. When there's a sunroof that's open, you see the bottom, there's so much noise in this image. It's not very pretty for conventional vision. But what we're looking for is, it's pretty blatantly wide. We can look at this and in a tenth of a second, we can see that there's one, two, or none, right? So why shouldn't we be able to train a camera quickly without a bunch of clicks to do that? Well, we can, and this is with our AutoLearn classify, which is kind of the intermediate step between what we can do with conventional vision and what we can do with true deep learning. So I will go ahead and show you all this tool. I'm going to double click it, bring it into my spreadsheet. You can see it defaults my field of view right here, but we're just going to look at the entire image, and we're going to even include all of the, kind of the bad lighting and all of that. So I'm just going to click OK. This is going to populate my sheet. And then what I'm going to do is click Collect Samples here. Now when I play my film strip, you're going to see my unlabeled number of images start to increase. So these are images that are feeding into my AI that I'm going to go in and I'm going to train into the network. Now, another main difference of what I'm showing you here, this technology, though it does run on the same hardware platform, it does not require the GPU-enabled PC to do the training. So if you're in this AutoLearn classify realm, we can get by without having to use a much higher-end PC. So now I've got about 24 images queued up, and I'm going to show y'all how easy this is. Now, again, I am looking at the entire field of view, so there's no patterns on any specific criteria here. And what I'm going to do is I'm going to add a new class, and that is a none, so we'll say none. And then what I'm going to do is click none, tell the software that has no sunroof. Now it's going to load the next image. What it does is it loads the lowest scoring image for next, so it's always trying to make the system better. So this one looks nothing like none, so I'm going to add 2. And I'm going to call that 2. So now it brings up the next lowest scoring out of those 24. This is a 1. It thinks 50% that it's a 2 because it doesn't know a 1 yet. So now I'm going to say 1, add it to 1. So from this point forward, we should start getting pretty good at determining what's what. So this one is a 2. It's fairly confident, but it's only seen 1 before. Let me make this bigger so you can see what's going on. Sorry about that. So this one is highly confident that it's a 1. I'll click that. None, nearly fully confident. And you can see down here, as I'm showing these worst case items in a row, my model health down here is displaying, based on all of the data set and all of our classes, it's going to be more apt to pass or more apt to fail properly. So 2. So you can see now my model health just went from 90 to 96. That's a 1. It's fairly confident. So, I mean, we can do this all day, or we can go ahead and go to the images section. And what this is going to do is it's going to populate and say, here's what you labeled. Okay, are all these 2? That's 2, that's 2. Yeah, all those are 2, that's a 1. All those are none. So right now, in fact, this would be running at 100% based on those images. So as you can see, I didn't have to write any rules. I didn't specify anything. I've looked at the entire field of view. All I've done is tell the software, hey, these are a few different examples of a few different classes, and now it learns 100% of all of these. Pretty simple. So, and with that, that's pretty much the overview of where we're playing with deep learning, what technology we've got out there, and I'm more than happy to field some questions, software-wise, technology-wise, hardware-wise, whatever it is. I would love to hear questions.
Hi, my main question is, will your distorted OCR character recognition decode captions? You know, the security things on websites. Will it read a caption?
Like the reCAPTCHA thing?
Exactly. It looks very similar to what you showed in your picture there. Distorted, curved, varying lighting. You know, they changed the color also. But
That's it.
That would be a major application.
That is a fascinating question. I know. So I'll answer from my perspective would be we've not attempted that from my standing just because it doesn't fall in the factory realm. To answer the question broader relative to our technology, I know that whatever they use for that text and the way that they add features to it, I think it is meant to try and debunk this type of technology or automated reading technology. But that certainly is a fascinating question. Perhaps one more that if you like, we could talk offline for if there is indeed an application specific. But but yeah, that's a very interesting question because those characters can look, you know, very distorted, very damaged, that kind of thing.
Hey, Alex, Jim Link here. In the inspection of products, if objects you're looking at are varying in colors, like for instance, I worked for a period of time at a tire manufacturing facility, and there you're looking at black product.
Mm-hmm. Lighting
was you had to really apply lighting depending on what part of the plant you're in and what you were trying to inspect. Because rubber could, even though it's black, could be various different shades. And one of the challenges of vision systems 20 years ago was putting the right lens on there and the right light. And
That's
the right
right.
angle of the camera.
That's right.
This product right here, how does it differ from that? Does a lot of those challenges go away with this AI?
So certainly things are made better. I wouldn't say that it disappears completely. As I mentioned, the rule of thumb is you still need to see the defect. So for example, if there was a defect here and I'm washed out due to my lighting, we won't see it. However, with lighting fluctuation, the demo card example I gave, that is made to simulate that your lighting is not always perfect, but I can still see the defect. The lighting isn't bad enough to cover it up. So you do gain great lengths of improvement with the AI over conventional. Because if your lighting varies, you train all of that variation into your model. Now, when it comes to color, if you're using a a monochrome vision system for AI, you've got 256 grayscale values to work with. If you use color, you've got 256 for red, 256 for green, 256 for blue. So you actually get a lot more data complexity, which for defect analysis and those types of things is actually a huge benefit when you're in AI. So the ability, based on what I've seen in the field, for VIDI to see changes in color, it is more discerning than the human eye by a wide margin. Some things like even like a glossy metal surface where they're applying the thinnest layer of a primer without any UV properties or reflective properties. It's to the human eye, you can't tell what you're looking at, and we've had VIDI be able to successfully pick up primed versus not primed.
Do you have color cameras then? Because you
Yes, we do.
D900.
Absolutely.
Okay. So the D900 is not the only piece of hardware you can run this in then?
Well, the D900 comes in color or monochrome. The slide that I showed on that may actually have been dated if it didn't show color as well. But yes, I certainly have color versions. In fact, I've got one.
I may have misread the slide.
What's that?
I just said I may have misread the slide. For some reason, I was thinking it was monochrome only, but I probably read it wrong.
Yeah, but fortunately, we do have monochrome and color, and they're all the same price. So you get to choose.
So when would you intentionally not use color? I'm trying to figure out why, if they're the same price, I wouldn't just always use color.
Sure. Yeah, no, that's a great question. So we use what's called a Bayer filter, and this is a little bit technical on just the like the camera CMOS technology, but basically each pixel in here is made up of subpixels. There's 2 green, 1 blue, 1 red. So when you have all of those pixels within, those subpixels within your main pixels, you functionally lose a little bit of resolution when taking your image. So if you needed to do very high accuracy measurement, maybe you're backlighting, you're taking a pen tip, putting it in silhouette with a backlight and measuring the tip point, you're going to resolve better in a monochrome camera than you would in a color camera. The other thing is speed. Monochrome cameras are a little bit faster. If you just need to read characters at a high rate of speed and you don't need to, detect color variations, then you would go with a monochrome. But that's an excellent question, and one that comes up really frequently since they are the same price. And, without speed constraints, a color camera does offer more. So that's a great question.
So these are rather simple mechanical examples that you give us. It works great. I'm surprised at the small size of your training sets. For something much more complex, like what you showed us initially, a cat, something biological, how large would the training set have to be then?
Yes. I might have to tiptoe because, of course, non-competes, NDAs, things of that nature. But there is a food product that is consumed by most carnivores, probably all carnivores, that is being picked and moved and manipulated and all types of things. And we're using the software to identify, positions, features, defective areas, grading, those types of things with this particular subject. And, some of those types of things take a few hundred to a few thousand to get all of the variation, the various types of things that you would see. So yeah, certainly the more complex the problem or the more variation you have within the problem, I think is the better way to put it, the more image sets that you would need.
Together, those image sets, do you have to be online with the computer? Or can you do it, does the camera store the images?
That's a fantastic question. So the camera itself has the built-in micro SD card slot. So you can save images to the camera, several thousand images, and then you can pull them off of this and put them to the camera, or you can be live connected with the camera as I am. And as I clicked my record button, these images are now on my computer. You can see there's my C users, da 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 da. And the other option, if either of those don't work for you, you can FTP. So you could put this on the network and FTP out. We can even change the file name to be, a date and timestamp or serialized with a barcode or something of that nature. If we're reading characters, we can call the file name the characters that were read. And then what we do, and this question hasn't come up yet, but I usually expect it, is when we have those images, how does the system train? Does it train automatically and get better with every trigger, or how does that work? And the answer is, because this is a factory floor device, if we had an auto train where we just looped in new information, if garbage somehow got in, it would pollute the system and then our line would be compromised. So, the way that we get around that, and this is kind of, for security, is you physically have to go in, add your images, and then click your train button to establish your new neural network. So that way, it takes consciousness to go in and make sure you've identified everything properly, and then you've actually retrained so no junk gets into your network. Now, in the event that something did get in, let's just say that we called this good, we can always go back and change it later, or we can simply remove the image. So you're not compromised if you accidentally put the wrong thing in your data set. And let me drag this back in. Go to my database overview. Let's just say we came in here and we did call this good. Now you can see, well, based on my thresholds, I have called this good, but the AI has said, no, this is really bad. So you've told me it's good, but I'm calling it bad. And it would show this on the screen. So you have, when you're looking at thousands of images or hundreds of images, it's very difficult to understand where you're at, but these kind of tools give you the ability to visualize that.
You're training thousands of images. What's your training time?
So it's not linear. I was confused at this at first. I thought thousands of images, if it's taking me 3 minutes to train this way, it's going to take, 6 hours. It actually doesn't. I've trained, I've got an OCR project right now, 5 megapixel images. I trained 4,000 images in about 5 minutes. So it really doesn't increase that much at all when you stack several thousand images on top. And I don't understand that, so I can't even speak to it, but it doesn't, it's not linear.
Is your software only available for Windows?
Yes, Windows 10.
Don't score 11 yet?
I believe Inside Vision Suite is Windows 10 only.
We're gonna skip that one, yes,
I assume, however, it'll support any flavor of Windows 10, so if I want to use LTSC or something like that, no issue.
I believe so.
estimated process?
Yeah. So as you can see right here, this is my cycle time. So typical typical rule of thumb for VIDI is 2 to 10 inspections a second, and it's going to vary based on which tool you're using, which resolution you're using. If you're doing full frame defect, complex defect inspection with a 5 megapixel camera, you know, it's probably assuming about 2 frames a second. If you're doing very small ROI OCR, 2 megapixel, then you're probably, you know, at the 10 or even faster than that. But it certainly doesn't run as quickly as like a conventional pattern tool. And I can do a get time on my detect tool right here. If it's going to tell me. Yeah, so that tool is running about 125 milliseconds. Now, I will point out, this is our Insight, you know, yellow camera, easy point and click vision. We do have our PC solution that still runs VIDI. That can be done much quicker, but the trade-off is you no longer have the spreadsheet programming interface and you're in Cognex Designer. So if you do have high-speed applications where you need deep learning, we can certainly talk about those. It's just going to be, you know, a lot more on the integration side.
Seen where they use multiple cameras and they stitch the images together. So if you wanted to do a round object, you could get a picture all the way around.
Mm-hmm.
Does
Yeah.
this work with that as well?
That would in the PC based, yes. Yeah, in the Insight based, you'd basically just take multiple cameras and take different vantage points, and they would inspect individually. But if you wanted that full unwrap, then we'd be in the PC world. But yes, we could do that.